Good? Good there? All right. So the front, the first page here is pretty straightforward. We can understand how to do that. Then I'm going to start to get out of control. Take a look at this one. Sulfur hexafluoride, SF6. You're not going to like this one. Counting the number of electrons, sulfur has 6. There's 6 fluorines, each having 7 electrons. So 42 plus 6 is 48 electrons. Oh, that's a lot. Fluorine can't go in the middle, so sulfur has to. So here it is. All right, there it is, sulfur. Attach the peripheral atoms with single bonds first. But we have 6 peripheral atoms. What are we going to do about this? It's not going to feel right, but yes, you're going to put them all on the sulfur. So let's do that. 1, 2, 3, 4, 5, 6. Great. This doesn't look right. The sulfur doesn't have 8 electrons. It's got 12 electrons around it. But I'm going to tell you something. It is correct. I mean, what else could we do with that? Fluorine can only make 1 bond. And I guess there's this idea of formal charge dictates that fluorine's only going to make 1 bond. If your central atom, listen to this, if the central atom is a 3rd row or larger atom, 3rd row or larger, so not carbon, nitrogen, oxygen, or fluorine, those are the 2nd row. If it's 3rd row or bigger, those atoms are big enough to be able to expand their octet, not their octet, their valence shell. They can expand their valence shell and have more than 8 electrons on it. I know we call it the octet rule, but there's a number of exceptions to it. And this is going to present one exception to the octet rule. So, yes, I know the sulfur has 12 electrons on it. Normally we're looking for it to have 8. But when we go ahead and add the peripheral fluorine lone pairs, you count them up, 48 electrons. So all the fluorines have 8 electrons around them. It's just that sulfur in the middle. And again, as long as sulfur is 3rd row or a bigger atom, then it's fine for it to gain more, or to have and live with more than 8 electrons. That's strange. Okay, next one I have for you is, oh, look at this one. A xenon compound. Xenon's a noble gas. We've always been taught that noble gases don't make compounds. Well, they didn't until now. And this is a real thing. Xenon difluoride is a thing. And we're going to do the dot structure of it just like we do any dot structure. Xenon has 8 valence electrons. Each fluorine has 7. There's 2 of them. 14 plus 8 is 22. Okay, we're looking for 22 electrons. So let's put the xenon in the middle. Normally, the first element written in the formula is what the central atom is. So let's get the xenon in there. Okay, you got 2 fluorines to put on there. How about like that? Spread them out. Get 8 electrons around everybody. Okay. Now count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 20 electrons shown. Everybody's following the octet rule, but I need 22 electrons. So what am I going to do? Where am I going to put 2 more electrons when everybody already is following the octet rule? That was what I was referring to back here. You need more electrons? Yeah, we need 2 more electrons. You have to put them on the central atom. I know it makes you feel dirty, but you got to put them on the xenon. Even though the xenon has 8. Now, there's not even a good place to put them. I don't know. How about there? But that's correct. This is absolutely right. It's the xenon that winds up. Now, count them. The xenon has 10 electrons around it, but it's fine. It's 3rd row or bigger, so it's perfectly legitimate for it to expand its valence shell to have more than 8 electrons on it. All right, I got one more for you. This one is actually going to require a little bit more of an explanation, but I'm going to save the more of the explanation for tomorrow. Let's just talk about this for a moment. The nitrate ion. Would you take a moment and try the nitrate ion? Sejal, is that your writing on Neha's hand? Oh. It reminds me of Sejal's writing. Very nice. We need 24 electrons in this one. Did you come up with a structure? And if so, does it have a double bond in it? Yes, it should. Yeah, when you put just single bonded oxygens around them and have all lone pairs around the rest of them, we have 26 electrons. We got to cut it back by 2. So that's where I erased 1 off the nitrogen, 1 off the oxygen, made a double bond, and that takes us down to 24. Now, does it matter which oxygen is making the double bond? No. Any of the 3 is fine. The last thing I told you, there was more explanation needed on this. Here's the more explanation. We look at this dot structure, and we see that one of the N-to-O bonds is a double bond, which double bonds are always shorter than single bonds because when you're sharing more electrons, it draws the atoms closer to each other. So this one, we would expect to be shorter than those 2 single bonds. But when this compound is analyzed, and there is a way of measuring bond length with a spectrometer, we find that the 3 N-to-O bonds are all the same length. How can it be the same length if they're not all the same bond? If I just said that single bonds are long and double bonds are shorter, triple bonds would be even shorter. These 3 are all the same length. How can that be? Well, I'm going to show you this. This is going to be picked up tomorrow. But the nitrogen is making the double bond on the oxygen on the right. It could just as well be making the double bond on the other oxygens too. Those 2 would be just as reasonable as that one. I kind of have made my structure smaller as I went. But what we find is this. The nitrate ion could be this arrangement. It could be this arrangement. or it could be this arrangement, all just as likely. Yes? So it turns out that this phenomenon happens where all three kind of become averaged into one. And so rather than having a double and two singles, a double and two singles, and then a double and two singles, the nitride ion actually has 1 1/3 bonds for each oxygen. That extra additional bond is broken up into thirds there, there, and there. And there's a name for that. The same thing happened with the benzene ring that we learned back in September. Does anybody remember what that's called? You know how the benzene ring has alternating double bonds? And when we analyze benzene, it doesn't have 3 short bonds and 3 long bonds. It's got all the same length bond. And they're all like 1.5 bonds. It starts with an R. What? Mitch knows it. Just say it, Mitch. Resonance. It's resonance. Does that word come back to you at all? I know I used it. That was a few tests and quizzes ago. But yeah, the nitrate ion resonates among these three. What happens is it's like it becomes an average of those three structures. That's what resonance is. When you have a double bond that could just as likely go in more than one place, then the structure resonates among them. All right, I'll pick up resonance tomorrow. We'll talk about that more tomorrow. Yeah, we're down to the last within 1 minute.